Okay, so I'd like to talk more about combinatorial species, or just species that they're called, and their generating functions and using them to calculate things in combinatorics. So I forgot to say last time that there's different free books available online about this subject, and you can get a hold of them from my website. On my website, and then TWF, I've got the videos of all the old lectures I've given, and also reading material. And so there's those books on species available there. Okay, so there are all sorts of wonderful tricks you can do with species, but it takes a little work to build up the machinery to be able to do those tricks. So I have to get there. But so let me just remind you the key points from last time. So a species is a functor from the category of finite sets, which I call E, because we saw that its cardinality is number E, to the category of sets. So the idea is that this functor assigns to any set, any finite set, some set which we think of as a set of structures of some sort that we can put on that finite set. So each species is a sort of structure. So there's a species of graphs, there's a species of two colorings, and there are lots of others. And then from such a thing, we can do stuff. So if you hand me a groupoid, X, we get a new groupoid using our species, and I call that F hat of X. And the way this groupoid works is that we write down a kind of power series, but it's a categorified power series, meaning that all the symbols in here are a little bit higher level in meaning than you're used to in a power series, but this should remind you of a Taylor series. So what's going on here, we can take the product of two groupoids and get another groupoid. So we can take the groupoid X and get this new groupoid where the objects are n tuples of objects in the groupoid X, and the morphisms are n tuples of morphisms. We can take the product of that with the groupoid F of n. What's n? Well, n is a natural number, but remember, I'm playing this sneaky game of thinking of natural numbers as finite sets in the way that von Neumann came up with. So it makes sense to take a natural number, think of it as a finite set, and apply this functor to it. So this is a set, and we can think of a set as a special kind of groupoid. It's a groupoid with only identity morphisms. So here's a groupoid, there's a groupoid, the product is a groupoid. And because F is a functor, the group of permutations, Sn of an n-element set, will act on this groupoid. It acts on F of n because F is a functor. It acts on x to the n by permuting the entries in the n tuple. And so I showed you last time that when you have a groupoid and a group acting on it, you can take this weak quotient, which I didn't explain very much detail, except in the case of a set, but it's a weak quotient, meaning that we stick in extra isomorphisms for whenever you have a permutation that maps one object to another. So this should remind you of, this should have the look of a Taylor series. And so one thing we can do is turn it into an actual Taylor series of the traditional sort by taking the cardinality of everything. So I define this concept of the cardinality of a groupoid, which doesn't need to be a natural number anymore. Remember, the cardinality of a groupoid is you go around the isomorphism classes of objects, and then you sum up 1 over the cardinality of its group of automorphisms. So you get a rational number if it's a finite sum. And so here we just take the cardinality of everything. And oh, I forgot to say what this sum is. So the sum is called coproduct or disjoint union. So we have all these groupoids here, and we just sort of set them side by side and get this coproduct of groupoids. But cardinality of groupoids gets along with addition and multiplication and division. So the cardinality of the groupoid f hat of x is just the cardinality of f of n times the cardinality of the groupoid x to the n, and then divided by the cardinality of the group Sn, which is n factorial. So this follows from all the things we saw last time. And so this is an ordinary Taylor series where now you see this typical 1 over n factorial in the Taylor series. So the interesting thing is that this cardinality only depends on these cardinalities and the cardinality of the groupoid x. So we can make up a function that is this power series. That is, we can make up a power series. So we can invent a power series, and it's called the generating function of f. The generating function of our species f, like this. So I'll call it f hat with a vertical bars around it. It's not a cardinality necessarily, but we'll see that it's connected to this cardinality here. So what it is it's just, oh, sorry. This is the sort of power series that you could just put in a normal number in there. And so let me just tell you what you get. You just get this kind of thing that I wrote down on the line in the equation above, but now just the number x to the n here. So that's how you define a generating function. So basically, it's copying that, and then I was going to call it the cardinality of f, and in my last lecture I called it a lowercase f, but at that time, but then I realized that it's very hard to distinguish between first turning two letters into lowercase and then adding them, and then versus adding them and then turning them lowercase. So certain identities that this process obeys look completely trivial if I use that notation. So I made up. So I like this notation. But yeah, I spend like the whole week worrying about notation. So now you see why. So we define this, and thus what we get is that the cardinality of the groupoid f hat of the groupoid x is this function applied to the cardinality of the groupoid x. So I like this equation because we have conservation of hats, and you don't want to lose a hat, right? So yeah, so that's a trivial consequence of that, but it's very nice. Okay, so let me give an example. I want to give interesting examples, but I have to warm up with a trivial example. So let's make up a species called A sub n. And here's how it works. It's a very, very simple one. So if I stick in a finite set S, here's what we get. So we get the one element set, that is the set that I'm calling 1, if the cardinality of S is equal to n, and we get the empty set otherwise. Now, for this to be a functor, I really need to know how permutations or bijections act on it, but they act trivially because they're not any interesting permutations of a one element set. A zero element set, it's only the identity. So this tells you everything you need to know. So I said before that a species is a way of describing some sort of structure you can put on finite sets. But this is a sort of degenerate case of a structure, because this is some kind of structure that you can put on the set S in exactly one way if it has n elements, and you can't put the structure on at all, there's no ways, if it has any other number of elements. So this structure is actually a property. So a property is a structure that you can only put on something in one way. That's a good way to think about the difference between structures and properties, and that at most one way. And so I would call AN this, I would call it, I like this sort of slangy description of species. I would call this thing being an element set. So that's a property of finite sets. They can either be an n-element set or not. And so there's either one way for a set to be an n-element set or none. So it's a funny structure that's just a property. So we can look at its generating function. So first we can look at an hat of some groupoid x using this formula down here, right? So this sum here, in our example here, it'll be 0 or empty. It'll be an empty groupoid, except when n equals 1, and then you get a one element. You get the one element set thought of as a groupoid, and so that you just get 1 times this stuff, and so you just wind up getting wind up getting x to the n over Sn, right? And so what the hell does that actually mean? So this is some operation that you can apply to a groupoid, and what you do is you take the groupoid, you take its nth power, and then you weakly mod out by permutations. That is, you stick in extra isomorphisms for permutations. I could explain this in more detail, but I think I'll just march right on because I've got sort of limited time, and then just work out the generating function, and no surprise, it's just this. So this is like the grown-up version of this, and this is sort of like this standard nth term you see in a Taylor series if the coefficients are just trivial. Okay, we'll need that species later and its generating function. But we need to get other more interesting species than that to get anything fun to happen. So we need to have some operations for building new species out of old. So let's start talking about new species from old. So let's say we have two species, F and G. We can do various things to them to get new species. So first of all, we can add them. So define their sum. So how do we add them? So we're going to try to get some new species, F plus G, from E to set. And we do it in the sort of obvious way. So this is supposed to be something that eats finite sets. So feed it a finite set, and we define it in the obvious way that you've learned all your life as mathematicians, like this. So here, f of s is a set, g of s is a set, and this means the disjoint union or coproduct, as category theorists put it. That's just disjoint union. So the idea is that if F is some kind of structure that you can put on a finite set, and so is G, this is some new structure. And the way you put this new structure on a finite set is you make up your mind, am I going to either put a structure of the F kind on or the structure of the G kind on? And I do one or the other, but not both. It's an exclusive or. So this is like F structure or G structure, but exclusive or. So like I could decide to put the structure of a graph on something or the structure of a 3 coloring on it. That's some weird, crazy structure that's a graph or a 3 coloring, exclusive or. And the reason why it's good is because you can show, and I won't do it, but it's very easy. You can show that F plus G hat of any groupoid is F hat of that groupoid disjoint union of coproduct G hat of that groupoid. So addition gets along to this. And then using that, you can work out, do the next little calculation, and you can see that the generating function of F plus G is the generating function of F plus the generating function of G. So that's, oh no, 2 hats. Well, this is a very big hat, you see. It actually was 2 hats. So yes, I can never slip anything by, Tom. So, okay, great, we can add, yay. So now the next thing we would try to do is to multiply. This turns out to be much more tricky in an interesting way, not ultimately hard, but it turns out that there are like 2 ways to multiply, one of which is much more useful than the other. So there's something called the Hadamard product. So I'll call it F times G from, that'll be a new species. And, well, you can guess F times G of S, we just define it to be F of S times G of S. So here what we're doing is we're saying to put an F times G structure on a set, we put an F structure on it and also put a G structure on it. Because remember, this is a set here, and these elements of it are ordered pairs. So like if F is graphs and G is 2 colorings, to put an F times G structure on a set, we make it, we 2 color it, and we put the structure of a graph on it. So it could be something like this. Now, that sounds like a great idea, but it turns out that it's a little bit weird, because when you work out what it does to how it gets along with generating functions, it gets along with it in a somewhat funny way. I'll just skip over straight to the generating function and tell you what it is. And basically, so here I'm writing down the generating function. Sorry, I erased the formula for generating functions in general, but we do the generating function, but it's with F times G. So what we get is the sum over actual numbers of F of n times G of n, the cardinality of that, but that's the cardinality of the product of those 2 things. So we get this. And that's a little bit weird. That's something that you don't normally do. So it's not normally the way you multiply 2 power series is multiply them coefficient-wise. That's a weird way that you can multiply for formal power series, multiply them coefficient-wise. It makes them into an algebra. It's perfectly distributes over addition and everything, but it's not the normal way that you were taught in school to multiply formal power series or polynomials or anything like that. You don't, if you multiplied polynomials that way, multiplying them coefficient-wise, the teacher would just mark it wrong, right? So you can say, I'm using the Hadamard product. They would just say, forget it, you're wrong. So anyway, that's a thing, and it's mildly interesting, but there's something much more interesting often, which is some other way of multiplying species that gives you the usual way of multiplying power series, and that's called the Cauchy product for some reason. I have no idea why these are called that, but famous mathematicians just get things named after them. And this one is much less obvious to define, but it winds up to be nicer. So I'll write it with a different kind of multiplication symbol. So here's how this works. I'll tell you what f dot g of a set is. So what I do is I look at all possible ways of chopping up the set into two disjoint subsets. So I'll take all subsets T of S, and then I'll look at f of T times G of S minus T. So this turns out to be the good thing. So what are we doing here? What we're saying is to put an f dot G structure on a set S, I take any way of chopping that set into two parts. I put an F structure on the first part and a G structure on the second part. So for example, if I did the same example where F was two colorings and G was graphs, I could try to do something like that. So I have this set here that say has 5 elements, and I want to put an F dot G structure on it. So first I just chop it into two parts, the T part and the S minus T part. And then on the first part, I give that a 2 coloring. And the second part, I make that the vertices of a graph. So that's an F dot G structure on that 5 element set. Does that make sense? Okay, so now the question is, why should you care about this weird operation? Notice it's very non-commutative. Well, it's because when we calculate the generating function of this, it's just the product in the usual sense of the generating functions of f and g. That's why people like it. So let's figure that out. So let's take the generating function of f dot g and see what we get. So it's the sum over natural numbers of the cardinality of the set of f dot g structures on n divided by n factorial times x to the n. That's by definition of generating function. That's just the what, you know, you're looking at me like that was funny. Nothing funny has happened yet. I've just used the definition. Okay, sorry. I thought you were doubt. Sorry? Oh, hats. Right. I lost my hat. So so here, one hat. But this part of the definition didn't have any hats in it. Yes. It's not conservation of hats. Oh no. Well, I mean, if you're defining hat without a hat, then you're in trouble, right? So okay. So then I used the definition. Thanks. No, I just didn't interpret your quizzical look at first. I knew something weird was happening, but I didn't know what it was. Okay, so now here I use this formula, but now S is this set we're calling N. So we get f of so we're going to sum now over all subsets of that n element set, and so we get cardinality of f of t times the cardinality of g n minus t. Remember, n is a finite set, and t is a subset of it. So we get that. And then we notice this. There are lots of different 3-element subsets of n, but so T could be like all sorts of 3-element subsets, for example, but the cardinality wouldn't depend on which 3-element set you picked, because if T is isomorphic to T prime, the cardinality of f of T equals the cardinality of f of T prime. So we might as well just sum over numbers that are, let me call it k, that are less than or equal to n. So, and just look at, in other words, just look at the, so T could have various numbers of elements, and it could have any number of elements less than or equal to n. Let's call that k. And then this, the cardinality of n minus T would be n minus k. And then I'm dividing by n factorial. But that's not right yet, because there are lots of different k element subsets of n. And here I just talked about one of them, but there are n choose k of them. So I have to multiply by that. In other words, all these terms would be equal for various choices of T that all had the same cardinality k. And so we just multiply by that factor. So that's what we get. And then, sorry, I don't quite know where to put the word. But then we can play around with this expression using the formula for the binomial coefficient. Namely, n choose k has an n factorial in the numerator, which cancels that one. And then it's got k factorial and n minus k factorial in the denominator. So a much more pleasing way to write this is like that. You can tell that's nice, right? And so it's good. It'll look even better if we make up another name for the number n minus k. Let n minus k be L. And so summing over all these choices of n and k is the same thing as summing over all possible choices of k and L. So we can just sum over all k and L in the natural numbers. And then say this, we get f of k over k factorial, and then g of L, cardinality of that, over L factorial. And then n, of course, was k plus L. So we can take this x to the n, and we can break it up into an x to the k and an x to the L, like that. And now we're really happy, right? Because this just can be factored into the product of two power series. The power series that looks like this first stuff, and the power series that looks like the second stuff. The first one is just the generating function f hat of x, and then the second one is just g hat of x. So lo and behold, it's working, right? So this funny Cauchy product operation is giving us the usual product of when we take generating functions. So in short, what we're seeing is that the generating function of f dot g is the generating function of f times the generating function of g, where this is the usual multiplication of power series. So that's nice, because there's all sorts of tricks we can do with power series, and we tend to want to use the usual way of multiplying power series when we're playing those tricks. Okay, let's use this for something now. Yeah. I don't even know what that is. What is it? The component-wise product? The entry-wise product? Yes. Okay, then yeah, it's sort of like that. So I guess if Hadamard was so stupid that he multiplied matrices entry-wise, he would probably could like name the idea of multiplying polynomials coefficient-wise after him too. He obviously failed his way through math classes, but no, those operations probably actually are interesting. They're just like a little bit less interesting than the famous ways of multiplying things. Yeah. So yeah, now I'm really curious about the history of that. So let's calculate. Let's use this to do something here. So let T be the species. I'm going to talk about finally a really interesting kind of structure that you can put on finite sets. I'll call it the species of trees, but there are lots of kinds of trees. So these are actually going to be binary, planar, rooted trees, but I'll just say trees. So, for example, I'm not going to define that in detail. I'll give you an example. So like, say S is some finite set, 0, 1, 2, 3, 4. So say I want to put a tree structure on that finite set. What do I mean by that? Well, there are lots of things I could mean, but what I mean is that I'm going to make these elements here be the leaves of a tree of this sort. So I will draw a tree, and so the tree here has a root, and then it's drawn in the plane, so you can always talk about which edges are left and right of a given node, and it's binary, so there can branch it either branches twice or not at all. And let's see, so the hard part is for me to figure out how to draw one that has 5 leaves. Yeah, that has 5 leaves there, and then those will be the elements of our set. So we could stick the numbers 0 through 4 in here in any way we want. And so this is an example of what I mean by a tree structure on this set. I'm discussing a tree structure, making it into the leaves of that tree. So you could try to count the number of tree structures on an element set. That's a typical thing that combinatorists like to think about. So let's do it. So the way we do it is we think about this species and think about how to relate it to other species, but in fact, we'll relate it to itself in the following way. So notice I claim that this species here is isomorphic to sorry, hold on. That's probably not what I mean. I don't know. Yeah, it is sort of funny. A1 plus T dot T. So what the heck does that mean? It's saying a tree is either a one-element set. Remember, this species was being a one-element set, or it's a pair of trees. Now, one funny thing that I didn't tell you about, which seems sort of weird, seems extremely weird at first, but there's one case of this definition of tree. It's a little bit different than all the rest, which is what's a tree? What's a binary tree with just one leaf? I mean, there's also the question of no leaves, but and you might say, well, there's obviously no binary tree with just one leaf, but in fact, I'm going to declare that there is. I'm just going to do it. Okay, you can't stop me. So I feel guilty, but it won't stop me. So there's a tree with just one leaf, and it looks like that. That's weird, right? That doesn't have a root. Okay, it's weird. Okay, and there's also there's no empty tree. Oh, good. Okay, it's normal. No, but we're not. Notice we're not. It is the root. Ha ha ha. Yeah, is that it? So normally the leaves are not the same as the root. But Tom is smarter than me, so he realized that the leaf could be the root. That's a tech, and okay. And then you could number it. You could, yeah, okay. Okay, great. Yes. So a very tiny tree, the leaf is the root. Okay, yeah. Yeah, good. That reassures my faith in reality. But I was just gonna like, you know, sometimes people say like by convention, blah de blah. And then if you think hard enough, you say, no, it's not just by convention. It's just like if you carefully think about what you're doing, that's how it works out. Right. So, okay, good. So yeah, there's one. So a tree is either this weird little tree where with one leaf that is the root, or it's not. And if it's not, then it has to have this stuff. And then there's going to be a tree up here and some other tree over there. So this is just saying a tree is either the silly little tree or it's the same as a pair of trees. So it's a recursive definition, inductive definition of a tree. So now what we can do is take the generating function of that equation, of everything in that equation. So the generating function of t is equal to the generating function of a1 plus the generating function of t hat dot t hat. But we've seen that the generating function, I worked out the generating function of a hat n, and I got x to the n over n factorial. So that's just 1 when n is 1. X, I can't do x. Oh, God. Yeah, thanks. X to the 1 over 1 factorial is x. And then this is just p hat squared. So we get this. And I'm here, of course, I mean, this is some power series in x. So I mean, if you wanted to, you could also write it like that if you want to be clear that they're all functions of x or power series in x. But I'll just write it as t hat with a bar around it, because now we can solve this thing for the generating function. So we can get all the t hat stuff on one side. And so now I'm going to write it in this more abbreviated way. We get t hat squared minus t hat plus x equals 0. So notice that's the thing we could not do at the level of the species themselves. We are not allowed to subtract species, but once you go down to the world of generating functions, then the power of subtraction is available to you. That's sort of, in a sense, why we decategorify. We like numbers because we can do cool things with numbers that don't make sense for sets, or at least maybe Tom could figure out how to do this because he knows about things with negative cardinality, but I'm not getting into that. I don't know if I know how to do that. And then we can say, hey, I know the quadratic equation, so I can solve this thing. And so I get negative b plus, or I have to say it out loud, negative b plus or minus the square root of b squared minus 4ac. Don't be confused by the fact that c is x, right? Over 2a. So lo and behold, we figured it out. And maybe now I will again admit that he had some power series in x. So there, that's it. What the hell is that? Well, first of all, we better figure out about this plus or minus business here. One of them is the right answer and one's the wrong answer. So we could, yeah, sure. Whoops, sorry. Sorry.
So you said the one element tree, or it could be two different trees.
Yep.
Okay, but actually a tree could either be empty, or the one element tree, or the stuff. But then it's more working because I was just adding 0 there, but I feel like it doesn't work so well when you start saying.
Yeah, this stuff can like drive you crazy, but I think the idea is that really that we're working with rooted trees in this story all along, and the tree has to have a root. So there's no empty one. Yeah, that's right. I mean, you could do other things, but this seems to work out pretty well. You could also play a game where instead of making the elements of your set be the leaves of the tree, you could do one where you make it be all the nodes of the tree. And then you get a somewhat different story that actually is related and gets me confused because it's related. But here we go. So now one thing you can do is you can notice that if you work out what t hat of 0 is, so remember, it's this power series. This is just the definition. But with 0 in there, what Well, as you all know, 0 to the 0 is 1. And so we just get the constant term. So this is just t of 0. By the way, Knuth made a really good point. He said, like, there are people who say that like 0 to the 0 is undefined, and they just go around telling students 0 to the 0 is undefined. But that means that like you're not able to ever evaluate any Taylor series at 0, because then you need to know what 0 to the 0 is for that. And the only way you get the right answer is if you define 0 to the 0 equals 1. So like for example, the binomial theorem, you can't like state that accurately if you don't know that 0 to the 0 is 1. So anyway, by convention, I'm defining 0 to be 1. I mean, it's also just true, but so anyway, so this is what you were just asking about, the cardinality of the number of ways you can make a 0 element set into the leaves of the tree, and we've agreed that there are none. So that's 0. So that means that this has better be a minus sign, because that's the only way that you get 0 when you set x to be 0. So that's it. Okay, that's nice. Now, what you can do is use this to actually count trees of this type that we're talking about. Yep. I've thought about them, but I haven't gotten anywhere yet. I think it's connected to Galois theory, because when you have like multiple solutions of polynomial equations, so you have like multi-sheeted Riemann surfaces, and the different sheets get interchanged by Galois transformations. So I think it has to do with that. But I really don't really get what the other solution would mean here. Yeah, I want to figure that out. Yeah. Well, that's a good question. So what I was really doing all along with these power series is not worrying about convergence at all. So I think I did mutter the word formal power series sometimes. So a formal power series means a power series where you don't demand that it converge at all. It's just a perfectly fine formal entity, and you can add and multiply them. But nonetheless, sometimes it turns out to be really interesting to evaluate them. And this one you could evaluate only wisely or safely when x is less than a quarter, I guess. Yeah. But it's definitely fun to be unsafe too, and we'll talk about that. So, but not yet. So what we're getting here is that if I write out the definition of this left-hand side, just to remind myself what it was. So this is the number of tree structures on an n-element set in the sense that we're defining. And then we're saying that we know what that, so that's a power series, and we're saying that it's equal to this thing, but we're thinking of this thing as a power series. Now, if I had more time, I would actually just grind out the Taylor series of this for you. I love calculus, actually, and this is like a chance to prove that I still remember it, but I'm not incredibly fast at it. So you have to like figure out the pattern of what happens when you keep taking the derivatives of this thing. And it's a lot of fun, but I don't have time for that much fun. So this is math after all. Not kind of too much fun. But nonetheless, you could stick it in Mathematica or whatever, and you could work it out. And I'll just tell you, let's see, I'll tell you how it starts out. So the point is, one can do this kind of calculation. It's not.
You can just use the binomial.
Yeah. Yeah. Right. Yep. So we get this kind of, we get some pattern, and it happens to look like that. And what's going on here is this. If I start drawing binary trees with different numbers of leaves, I get various choices. Sorry, I didn't leave myself enough room. Sorry, this is annoying. So there are 2 there. There are 5 here. Well, I really didn't leave myself enough room for that, but you can draw. It's fun to draw like the five ones there. Now, these numbers here, these coefficients here, they're called Catalan numbers, and they're very famous. And you could figure out a formula for them if you actually did use the binomial theorem or just differentiate, guess the pattern, prove it's true by induction. So these coefficients, the nth coefficient here is called the Catalan number, Cn. I hope I'm not making a fence post error. Sometimes I don't know, sometimes I think it's Cn plus 1 or something like that, but it should be called Cn, and I think it is actually. And so the point is you can work out the formula for them very easily just by differentiating this thing. But what we're getting, though, is something a little sneaky, because we're getting that these Catalan numbers are equal to these numbers divided by n factorial. So you have to be a little bit careful. There's an n factorial lurking around. So what we're getting is that the number of tree structures on the n element set is the nth Catalan number times n factorial. And at first that might seem confusing. I've sort of almost tried to confuse you by the way I was describing this. So where does that n factorial come from? Why aren't there just like 2 ways to put a tree structure on the 3 element set? Here they are. How come I'm saying it's like 2 times 3 factorial? So where's that factorial coming from? That's the question. Labeling, yeah. So we're putting these tree structures on an n element set, and what that means is we're making the tree, we're using the elements of that set to be the leaves of the tree. So if our 2 element set is like 0 and 1, we really get two different ways to put a tree structure on the 2 element set, 0, 1, and 1, 0. And so here we'd have to multiply this by 3 factorial and so on. So that's where that's coming from. So this comes from labelings. Ways of permuting the labels. So if you don't care about the labelings and you just want to count the pictures of trees without labels, then you got to divide Tn by n factorial and you get the Catalan numbers. So that's an idea of how this works. And the point is that this is a very general technique. What I did was I took a more or less arbitrary species that was defined recursively and then used some math to calculate its generating function. But you could do other things. You could do something like this, and you get some more interesting kind of structure. Maybe not so interesting. Stick the 2 in there, and this would be like trees where each branch, either 2 trees could pop out, or 3. So that'd be like binary or binary/ternary trees. And you could repeat this, and it's just harder because you have to solve a cubic equation, and it gets to be more of a mess, but you still can grind them out. Now I just want to finish with one last little surprise. So here we have this funny, nice formula. And remember what this was. This was the cardinality of the groupoid T hat of x, if x was a groupoid whose cardinality was little x. So if you have any groupoid whose cardinality is little x, then supposedly you get this formula. But there's something funny that happens when the power series fails to converge. For example, one of my favorite groupoids has cardinality 1, namely the one element set, thought of as a groupoid, has cardinality 1. And so there's this very nice groupoid T of 1. And what this is it's just the groupoid of trees. I mentioned a while back that things like T of X would be the groupoid of trees whose leaves would be labeled by the groupoid X, but if there's just one labeling, it's just the groupoid of trees. So apparently what we're getting is that the cardinality of this thing is 1 minus 3i over 2, sorry, square root of 3i over 2. Or in other words, e to the negative pi I over 6. It's a cube, it's a 6th root of unity. Pi over 3, thanks. Okay. Is that really right? Yeah. So positive real. Oh yeah, pi over 3. Some idiot made the circle be 2 pi around, right? Okay. So yeah, so it's a 6th root of unity, but it has a 3 in there, right? Yeah, okay. So now that doesn't make any sense at all. But you notice that like a lot of things we've been doing didn't make any sense at all for a while, namely like things with cardinality 1/2, things with cardinality E. So here, by going beyond the realm of the radius of convergence of this power series, we're getting something that's sort of wacky, but maybe there's some sense in which it makes sense. And I think I'll quit there, even though there's tons more to say about that, and Tom has worked on it a lot, but I got to quit. So if you have any questions, at least there's like a minute or two for questions before they kick us out. Thanks. Yep.
Can you do the same trick with planar antisymmetric binary tree?
What does an anti-symmetric binary tree even mean?
When you flip 2 branches over, you get a minus sign.
Minus sign, I see. I don't know. Yeah, I don't know. I would try to, if I tried to do something like that, I would start using not these set valued species that we're using now, but I'd use vect valued species. And then you can, then I think you might be able to make sense of that question. Yeah. So, and get minus signs coming into the picture. I'll think about that. Yes. It is. The most interesting thing is that see here we seem to be getting this weird idea, this weird thing that this, see, the 6th is 1, right? But it turns out that I guess Levere and Andreas Blas noticed that like you could also, of course, think of it that way. And then that way actually they showed that there's a very nice bijection between these groupoid, which is actually, by the way, this is a groupoid that just has no interesting automorphisms. I forget. That you actually get this. So they got a specific bijection between 7 tuples of trees and trees. And I think Blas has a great paper about this called something like 7 trees in a tree. What's it called, Tom? 7 trees in 1. Yeah. And so Blas showed that you can systematically get a hold of this bijection from this kind of nonsense. I mean, I'm calling it nonsense because it seems like it doesn't make sense. And then Tom Lenster and Marcello Fiore generalized that a lot and wrote a paper about that. And what's that one called? Or what's the what? Yeah, so there you are showing that in some contexts you can assign something like a cardinality to an object in a category, which could be a complex number. And if the complex number obeys some kind of algebraic equation, then you can actually get an isomorphism that instantiates that equation. I think that's a rough description of what they do. So that didn't really answer your question about analytic continuation. It just means that there is some like substance to this idea. It's not just like a stupid, wild idea that doesn't go anywhere. But I would love to understand better how the analytic continuation and the different sheets of these Riemann surfaces show up. And I don't really know. Yeah. No, there's just like a specific procedure that if I give you a 7 tuple of trees, if you're smart enough, like your boss, you could turn it into a single tree. And then that would be a bijection between 7 tuples of trees and trees. It's like an algorithmic, completely, I mean, I guess you could say it's like Hilbert's hotel because there's countable sets, but still, it's not a dirty trick or anything like that. It's just like a very clever bijection between 7 tuples of trees and trees, which he actually derives from thinking about these ideas. Yeah, so it's really cool. Okay, and Zoom folks have any questions? Or they're probably like, they're quiet. Well, yes, they're always quiet. Okay, bye, Zoomies.